on theory and practice, and we're going to have a mix of papers. We have 2 papers in the industry track, and then 4 papers in the regular paper track. We have a bunch of very good papers that are addressing key topics in the field. So, and let me remind for those of you attending remotely that you can post your questions on the Q&A area. You don't need to wait to the end of the presentation. In fact, there is a delay of a few seconds, so you can start posting your questions as soon as you wish. So I'm Pablo Castells from Autónoma University of Madrid. I will be the chair of this session. And our first presentation is going to be presented by Harald Steck. And the title is, hey Harald. The title is Negative Interactions for Improved Collaborative Filtering. Don't go deeper, go higher. You can start anytime.
Okay, hi, I'm Harald, and this is a joint work with Dawen from Netflix. So the motivation for this work was the fact that modeling high-order interaction can improve recommendation accuracy. To this end, we wanted to better understand 2 questions. First, what is actually captured by the higher order interactions learned by the model? And second, which users do actually benefit the most from adding these higher order interactions to our model? To keep it simple, we consider a linear model here. So we assume that the user item interaction matrix X is given. So in the simplest case, this is just a binary matrix where the entry 1 denotes that the user U interacted with the item I. Alternatively, one could also use some continuous values like the time duration a user watched a video. So in this linear model then, this matrix X gets multiplied by a learned item matrix B as to predict the scores for all the users and items. So when we write this model as an equation, then we can see that the learned item matrix B captures pairwise relations between the items I in the given user item interaction matrix and the item J for which we want to predict the score. So the predicted score is just the sum of the pairwise relations here. So now as to extend this model to higher order interactions, we can simply add an additional term, in this case here, regarding triplet relations that are captured by the learned matrix C. And these triplet relations have the form that the item J is now predicted based on the pair of items I and K. So to this end, we also need an additional data matrix Z. And here an entry UIK, it takes the value 1 if a user U played now both items I and K. So this matrix Z can also be generated from the given matrix X. We also tried to add even higher order terms, but we didn't find any significant improvements. So that's why we skipped them here. So we trained this model by minimizing the squared error, where now we replace the predicted scores by the given user item interaction matrix X as our target, which then has to be predicted by the pairwise and the triplet component of our model. As to prevent our model from learning trivial information, like predicting an item from itself, we have to impose a couple of constraints for the pairwise and for the triplet component. In addition, we also add some L2 norm regularization to prevent the model from overfitting. So we have now 2 hyperparameters, one for the pairwise and one for the triplet component. So this model can be trained by using ADMM, and details can be found in the paper. So this model can be viewed as an extension of the East model, which does not capture any higher order interactions, but allows for a closed form solution. It can also be viewed as a modified version of the HOSLIM model, which does model higher order interactions, but constrains them to be non-negative. So this is a key difference to our model, where we don't impose any such non-negativity constraints. Of course, one could also consider using deep nonlinear models, as they theoretically should be able to automatically learn these higher order interactions. However, in practice, it was found that this does not really work well, which then sparked additional research to develop special architectures like DCN v2 or the latent cross. Another drawback of deep models is that their low dimensionality in the embedding space can potentially create a severe bottleneck that may reduce the expressiveness of the model. So in our experiments, we follow the experimental protocol of Dawen Liang's paper from 2018 for reproducibility. In these slides, we just show recall at 20 as a ranking metric on 3 publicly available data sets. More metrics can be found in the paper. So the 3 data sets are the movie lens 20 million data, the Netflix price data, and the million song data. So they're all pre-processed according to Dawen Liang's paper in 2018. So when we now compare the baseline pairwise Ease model with the higher order model, then we can see that there's a considerable increase in the ranking accuracy in all 3 data sets. On the other hand, when we constrain our higher order triplet relations to be non-negative, like in the HOSLIM model, then we can see that the gain is only about half as large. So this shows that using negative interaction is very important in practice. So I'd like to just briefly show this slide that compares our simple approach to various baselines, including many nonlinear autoencoders. More information can be found in the paper. It's worth pointing out that on the MSD data on the right-hand column, which contains the largest number of items among the 3 data sets, this simple approach outperforms all the baselines by a large margin. So now, what is actually captured by these higher order relations? So to that end, we created a histogram of the predicted scores across all the test users and items, as can be seen in this plot. And then we split it into its pairwise component and its triplet component. And as we can see, the pairwise component skews to large positive values, whereas the triplet component skews to large negative values. So this provides a downward correction to the predicted scores. In other words, the predicted score of an item grows in a sublinear way with a number of similar items that the user has played. Finally, which users do actually benefit the most from modeling higher order interactions? To this end, we split the users based on their activity. That means the number of videos they played in the Netflix price data into 5 buckets, which can be shown in these, seen in these 5 plots. On the y-axis, we have the ranking metric NDCG at 100. And as we can see, the less active users benefit a lot from these higher order interactions compared to using the baseline Ease model. On the other hand, for the highly active users, the situation is pretty flat within the confidence intervals. So our hypothesis is that because the triplet relations are more prevalent among the highly active users, this actually frees up the pairwise relation to better adapt to the less active users, which hence benefit. So in summary, we considered a simple yet effective full rank model with higher order interactions and observed significant gains in ranking accuracy. So our key experimental findings are that the learned pairwise relations skewed positively, whereas the triplet relations skewed negatively in our experiments. So we saw that the negative higher order interactions are crucial in practice. And finally, and a little bit counterintuitively, the recommendation accuracy improved the most for the less active users rather than for the highly active users. So thank you for your attention. I'm happy to take questions now.
Thank you very much, Harald. So we do have some questions from remote participants. So first, there is a question by Jay. If you use the triplet set, the memory you need will be much bigger. So do you have a good idea to deal with large data sets other than increasing memory?
That's a good question. So I skipped about that in detail. So clearly you have this combinatorial explosion if you look at all that, triplets. What we did is we just used a subset of them. And the way that we chose a good subset, we tried different possibilities. It's also outlined in the paper, is that we just use, if you remember, so we have this triplet that has basically ik as a pair to predict j. And so we just look at pairs ik, which occur most frequently in the data. And those are the ones that we use. So we try to use 1,000, 2,000, 5,000, up to 40,000 of these pairs. So that doesn't increase the memory too much. And then we saw that there's kind of a diminishing return. So that means we don't really need to use too many of these interactions to actually get most of the benefit.
Thank you. There is also a question from Parvez Rafi. Does the model address the sequential nature of higher order interactions? Like, for instance, you like item 1 before or after item 2. Is there any notion of sequentiality?
No, so at the moment, this model doesn't consider any time ordering. So it's just a bag of words or bag of interactions. So that could be a possible extension of this model, but I haven't thought about it yet.
Mm-hmm. Okay. Okay, I would also add a question of my own. So in the paper, maybe in the presentation you didn't mention, but you were trying to see, I mean, you got different results for different data sets, right? So the Million Song, Netflix, and Movie Lens, if I remember properly.
Right.
And we tried to find the reason why, so this approach works best, I think it was in the Million Song data set. And so you
so basically because it has the largest number of items. So Million Song data set has 40,000 items. The other two data sets have 20,000 items. And then on top of that, we also looked at some new metric we called effective catalog size, which is outlined in the paper. And there we see that the difference is not only a factor of 2 from 40,000 to 20,000, but actually this Million Song data set is much, much larger. Effective catalog size is about 20,000, whereas the other two have about 2,000 or 3,000 effective catalog size. And the idea is that these deep models, they have this kind of bottleneck architecture. And if you have a lot of items in the output and in the input, and you have to feed it through a very narrow bottleneck, then you may lose a lot of information. That's why these models get outperformed by this simple model that we propose, because it's a full rank model, so it doesn't really lose anything going through this bottleneck. Of course, you could extend this bottleneck in deep models, but the problem is then that computation time, it just sort of goes through the roof if you have a super large embedding space.
All right, thanks a lot, Harald. Let's thank the speaker again.
Thank you.